Hello, everybody. My name is Kevin Casada, and today we're going to be taking a look at my project, Euler's Infinite Mind. So, we're going to be taking a dive into one of the greatest mathematicians and physicists to ever grace Earth, which is Euler. So, a little bit about my project. I will be exploring Euler's history as well as his influence on mathematicians later on. I will also be exploring Euler's knowledge of infinite series, as well as the impact it had on those mathematicians. And the specific mathematicians we're going to be looking at today are Riemann, Cauchy, and Cicero. Now, a little bit of background information on Euler. He was born on April 15 of 1707 in Basel, Switzerland. And at an early age, he was noticed and he had a tutor, which is a very famous mathematician named Johann Bernoulli. So he attended the University of Basel and earned his master's degree early in life. Now, Euler didn't really want to become a mathematician at first. He wanted to follow his steps to be in the ministry, just like his father, but with the potential that most mathematicians saw in Euler, he ended up going into a mathematics degree. He also did service for Russia in the Navy, and later on he became a professor of physics at St. Petersburg Academy. Now, after he became the professor, in the mid 1740s, he became mathematics director at Berlin Academy of Science and Beaux Arts. He published his first book called Mechanica in 1736. And now, most of his main influences were Newton, the Bernoulli family, as well as other mathematicians and physicists. So that's just a little bit of Euler. It's not too much, but it's just a little bit of background on his early life. Now, let's take a look at the impact Euler had. Euler laid the foundation for modern mathematics. He was a revolutionary thinker in the fields geometry, trigonometry, calculus, differential equations, number theory, notational systems, and those notational systems include having the function notation of f of x, having the notation for pi, having the notation for e, and so on. He also is a pioneer to real analysis and complex analysis. Now, those are the biggest things in mathematics that are led through Euler as Euler pioneered through those. So he also did work on subjects such as astronomy, lunar motion, acoustics, mechanics, and music. Now, astronomy, acoustics, and music, those are a little bit more different than mathematics, right? Mathematics and physics. This just goes to show how much Euler had an impact on everything that wasn't just mathematics or physics. Now, let's take a look at something called the Basel problem. Now, the Basel problem is a very, very famous problem. So let's kind of break it down. What the Basel problem is it's a generalization of the harmonic series, and Euler later used it to prove most of his analysis of infinite series. With that being in play, he developed an interest in solving the Basel problem. The interesting thing about the Basel problem is the development of it. Let's take a look at the P series, for example. So we have the infinite sum of 1 over n to the power of p. Now, if we take a look at that, when p is equal to 1, this becomes the harmonic series, right? We know the harmonic series, so whenever that exponent is 1, this becomes a harmonic series. Now, one thing we know about the harmonic series is that it diverges. So we know that the harmonic series diverges. But what about when we have that exponent being 2? Well, that infinite sum of 1 over n to the power of 2, that's just the Basel. That's exactly what they were trying to find. They were trying to find the value of that summation. So now, like I said, the Basel problem is finding the solution to the infinite sum of reciprocals of squares. That's just the summation, the infinite sum of 1 over n to the power of 2. Now, this was already tried by multiple mathematicians, and as well as including those like the Bernoulli family. So it was extremely difficult because not everybody was able to find. Actually, no one was able to find a solution up until Euler came along. So when Euler first started developing this proof, or when he figured out what the answer was, it was a much less rigorous proof. All he put down was a couple of steps in notes and the answer. So this was an informal approach to what he got. Later on, though, this caused him to go back and prove it analytically, proving it with a more rigorous proof. So after the problem was solved, this proof helped Euler and others develop proofs for many P-series, including those right there with even powers. For example, 1 over n to the power of 4 was a very famous one that Euler did right after this Basel problem. Now, Euler's proof deals a lot with using the infinite product of sine and comparing it with the result of the Maclaurin series of sine. Now, as the proof follows along and as he goes through the proof, he ends up going back and finishing it, and he develops an answer to the problem, which is pi squared over 6. So Euler was able to figure out the value of that problem, and after this was when Euler started continuing more and more and more rigorous proofs. This proof pioneered the development of mathematical analysis. Now, let's talk about Riemann. Now, the reason we're talking about Riemann is, if you remember early on in this presentation, I was talking about 3 main people that were influenced by Euler. Riemann was one of them. So Riemann was a strong follower in using the methods Euler used to prove mathematical problems. He loved the infinite series. How do we know we love the infinite series? One of the biggest things he did was Riemann sums, or one of the most known things, not biggest thing, but one of the most known things is the Riemann sums. So he was influenced by Euler's method to determine his own infinite sum, which is known as the Riemann sum. Now, Euler's method, whenever we're using Euler's method, it shows a way of approximating values of a differential equation when the slope and a change in x are given. That being said, in order to find an area under a curve, this method uses smaller and smaller intervals of tangent lines between points to solve for the value. Sound very familiar? Absolutely. Something that we've already done before in calculus. We've known Riemann sums. Riemann sums do a very similar thing and get a very similar outcome. That's because Riemann was influenced by Euler's method to create his own infinite sum, but he just tweaked it a bit. He tweaked it and personalized it and made it his own. That was one of the things that Riemann got from Euler, one of the things that influenced him a lot. Now, another thing that we see is Euler's zeta function. Now, if you look to the top right, we have the infinite sum of 1 over n to the power of s as the infinite product of primes of 1 over 1 minus 1 over p to the power of s. That's Euler's zeta function. Now, what Riemann did with that was, with Euler's zeta function, we have certain bounds that we can't cross. If not, the function would be, there was nothing to that function there. But what Riemann did is he was able to expand the bounds of that zeta function to what we know as Riemann zeta function. And with that Riemann zeta function, he was able to develop his own Riemann hypothesis. Now, the hypothesis goes into depth of how to find critical points that critical points are only in a vertical line within those bounds. And that Riemann hypothesis is one of those millennial problems. It's a big problem. It still hasn't been solved, so it's still out there. Now, these are just a couple of things that Riemann was influenced by Euler. But the Riemann sums was one of the most important things that we're looking at, just because we're looking at infinite series. Now, another famous mathematician, Cauchy. Cauchy was a mathematician inspired by Euler. He continued exploring many things Euler started, and that gave him the foundation of becoming a mathematician. Now, one of the main things we're looking at is the Cauchy product of two infinite sums. Now, infinite sums, we've already seen that before. Euler, that's all he's been doing, right? The Basel problem, the 1 over n to the power of 4, those P series, harmonic series. He's been looking at infinite sums. Now, Cauchy kind of took it an extra step and said, let's take a look at the product of two infinite sums. So this came about by trying to prove the convergence of the two infinite series. So we have seen that Euler has produced multiple proofs on convergence. Now, we're seeing Cauchy prove the product of them. So how did Cauchy prove the product of them? This is how he proved it. Now, this method takes a little less time because instead of solving for an actual number, instead of having to go through the infinite series, we're looking at the bounds. So we look at the bounds of one of those series and then the other series. And because both of those series have bounds, then that means that the product of them has to have a bound, which means if they have a bound, then it converges. Right? This helps us determine that that product of two infinite sums converges. Now, how does this relate to Euler? Well, Euler could have used these product of infinite series proofs to prove the bounds instead of having to prove an actual value. So going straight into just solving certain bounds of those series instead of getting an actual value. Now, lastly, let's take a look at Cesaro. So Cesaro developed the proof of proving convergence by finding a limit for it to converge rather than finding a value. So kind of similar, but not so similar to what Cauchy did. Let's talk about what Cesaro did. What was the biggest thing Cesaro did with infinite series? Whenever we're looking at infinite series, there's some series that diverge. There's some that converge, some that diverge. Now, what Cesaro did was say, let's take some of those infinite series that diverge, and let's try to prove the convergence. And this is how he did it. So proving this deals more with finding the average of the terms. So first, what we have to do is we have to find those partial sums. So we take the partial sums, and now from the partial sums, what we're going to do is we're going to find the average of them. So let's take a look at this. If we have three terms that are three partial sums, what we're going to do is our first average is just going to be that first term, right? Because we're going to have that term divided by 1, so we just get that first term. Now the second average comes from the summation of the first and the second term divided by 2. That gives us the second average. And then the third average is the average of the first, or the sum of the first plus the second plus the third term divided by 3, and we get the average of that term. And from there, we can prove the convergence of it. This is a slight shift in work from Euler, Riemann, and Cauchy, but with similar impacts. Now, the reason being is that Cicero mean proves complex numbers converge by reaching that limit using those averages. This gets into complex analysis. Cicero kind of developed complex analysis as it is today, but a simpler method to use when proving that convergence. So let's take a look at the Grandi series. So Grandi series is the infinite sum of an alternating series, which is -1 to the power of n. Now, if we look at it, we have 1 minus 1 plus 1 minus 1 plus 1 minus 1. And we can keep on going, right? It's an infinite sum. It keeps on going. So now what Cicero did was, we know that this series diverges, right? How do we know it diverges? Well, let's take the partial sums. What happens if we take the partial sums? Well, the first term we get is 1, right? Because that's our first term. But what about if we add the first and the second term? We get 1 minus 1. That's 0. Now the third term, 1 minus 1 plus 1, we get 1. Then 1 minus 1 plus 1 minus 1, we get 0. Then we get 1, we get 0, we get 1. And it keeps on going right through that infinite series. So because we don't reach a certain number, then we know that this series diverges. So with that being said, we know this series diverges, but now what if we use Cicero's mean? What if we use that average? Let's go ahead and try it. So with Cicero's mean to the partial sums, right? We're not going to be doing it to our alternating series. We're going to be using it to that partial sums. What we end up getting is our first term stays the same. It's just 1, right? Because we have 1 over 1. Now our second term, we're going to use 1 plus 0. So when we add those two, then we find the average. So we divide it by 2. We get 1/2. And we take the first 3 terms, 1 plus 0 plus 1, we get 2. Divided by 3, that's our average. So we get 2 over 3. Now we take a look at the first 4. 1 plus 0 plus 1 plus 0, we get 2 over 4. That's just 1/2. And then we can keep on going. We look at the fifth term, we get 1 plus 0 plus 1 plus 0 plus 1. That's 3 over 5. And then what this ends up giving us is this term being 1/2, and then our next term being something closer to 1/2, and then 1/2, something closer to 1/2, 1/2. And it just keeps on going, where we end up converging to 1/2. This is a prime example of how Cicero's mean has been applied to one of the divergent series. And it's an incredible kind of thing that he did, just showing us that, yes, yeah, this series can diverge, but it can also converge. Right, now, in conclusion, we saw multiple ways Euler influenced a lot of mathematicians with his infinite series and harmonic series proofs. We saw Riemann. Riemann was able to develop a different understanding of solving areas under the curves with the help of Euler's method of differential equations, right? He developed it and made it his own. Now, Cauchy was able to develop a proof of convergence based off of the bounds rather than values of infinite series. So he created those proofs based off of finding bounds to solve convergence. And now lastly, what we just saw with Cicero, he was able to establish a proof of convergence by proving the infinite series has a limit through the average of partial sums. It doesn't necessarily have to converge right away, but we proved that we look at the partial sums and we take the average of those partial sums, then we can converge those series. Now, some of these are just variations of what Euler did. They're a lot similar to what Euler did, but just very, very smallly tweaked. right? Very personalized to each of those mathematicians and what they wanted to accomplish. Now, with that being said, Euler was a great pioneer to a lot of mathematical things that he did, and he was a great pioneer to the mathematicians that we know as Riemann, Cauchy, and Cicero. And with that, thank you so much for hearing out my presentation. I hope you guys enjoyed the presentation, and I hope you guys have a great day.